Hello everyone, I am Divya SJBIT working as assistant professor in the department of ECE, SJBIT. In the previous lecture, I have discussed about the sampling process. In this video, I'll be explaining about pulse amplitude modulation. Now that we have understood what is sampling process, we are now ready to formally define what is pulse amplitude modulation. It is the simplest and the most basic form of analog pulse modulation technique. In pulse amplitude modulation, the amplitudes of regularly spaced pulses are varied in proportion to the corresponding sample values of a continuous message signal. The pulses can be of a rectangular form or some other appropriate shape. Pulse amplitude modulation, as defined here, is somewhat similar to natural sampling, where the message signal it is multiplied by a periodic train of rectangular pulses. In natural sampling, the top of each modulated rectangular pulse varies with the message signal, whereas in PAM it is maintained flat. Natural sampling is explored uh, in the previous topics. The waveform of the PAM it is as shown in this figure. The dashed curve, this one, this dashed curve in the figure, it depicts the waveform of a message signal m of t. And the sequence of amplitude modulated rectangular pulse it is shown in the solid lines. This one, like this. So there are two operations involved in the generation of the PAM signal. The first operation is instantaneous sampling. Instantaneous sampling of the message signal m of t every ts seconds, where the sampling rate fs is equal to 1 over ts. It is chosen in accordance with the sampling theorem. And the second one is lengthening the duration of each sample so obtained to some constant value t. So in digital circuits, these two operations are jointly referred to as sample and hold. One important reason for intentionally lengthening the duration of each sample is to avoid the use of excessive channel bandwidth. Since bandwidth is inversely proportional to the pulse duration. However, we need to take care in about how long we make the duration t. So let S of t denote the sequence of flat top samples generated so we can write as S of t is equal to summation n scrum minus infinity to plus infinity m of nts into h of t minus nts, where ts is the sampling period, m of nts is the sample value of m of t obtained at the time t is equal to nts. So where h of t it is described as follows: 1 for 0 less than t less than capital T. Otherwise it is half when t is equal to 0 and t is equal to capital T. 0 otherwise. So where the sampled version of m of t is given by m delta of t, it is summation n is from minus infinity to plus infinity m of nts into delta of t minus nts. So here delta of t minus nts, it is the time shifted delta function. Therefore, convolving m delta of t with the pulse h of t, we get this equation, this form. This is your h of t, this is h of f, and this is augment of h of f. So we can write this as m delta of t convoluted with h of t is equal to minus infinity to plus infinity m delta of tau into h of t minus tau. So after suitable arrangements, we can write this as equal to n is from minus infinity to plus infinity m of nts into h of t minus nts. Delta of t is equal to m s of t modulated signal, it is equal to m delta of t convoluted with h of t. Applying the Fourier transform, we can write s of f is equal to m delta of f into h of f. So m delta of f, it is given by fs summation k is from minus infinity to plus infinity capital M of f m delta of f is equal to fs summation k is from minus infinity to plus infinity m of f minus k into fs. So we can see in this diagram here where fs is equal to 1 over 2s 1 over ts, the sampling rate, given a PAM signal s of t whose Fourier transform s of f, it is defined by that equation. The equation is s of f is equal to fs summation k is from minus infinity to plus infinity m of f minus kfs into h of f. So how do we recover the original message signal? And the final step in this reconstruction, we may now pass the signal s of t through a low pass filter whose frequency response is defined in the previous diagram. Here it is assumed that the message signal is band limited to the bandwidth W and the sampling rate Fs, and it is larger than the Nyquist rate 2W. So we find that the spectrum of the resulting filter output, it is equal to m of f into h of f. This output is equivalent to passing the original message signal m of t through another low pass filter of transfer function h of f. So that is depicted in this diagram. So from the previous equation, we know that the Fourier transform of rectangular pulse h of t, it is given by h of f is equal to t times sinc function of ft exponential of minus j pi ft. We see therefore that by using flat top samples to generate a PAM signal, we have introduced amplitude distortion as well as there is a delay of t by 2. This effect is rather, it is similar to the variation in transmission with frequency that is caused by the finite size of the scanning aperture in television. Accordingly, the distortion caused by the use of pulse amplitude modulation to transmit an analog information bearing signal is referred to as aperture effect. This distortion may be corrected by connecting an equalizer in cascade with the low pass reconstruction filter, as you can see in the diagram. You have a PAM incoming signal, you have a reconstruction filter and a equalizer. The output is the original message signal M of t. The equalizer has the effect of decreasing the in-band loss of the reconstruction filter as the frequency increases in such a manner as to compensate for the aperture effect. Ideally, the amplitude response of the equalizer is given by 1 over h of f. So 1 over h of f is equal to 1 over t into sinc function of ft. It is nothing but pi f divided by sine of pi ft. So this figure, it displays the ideal form of equalization needed for the example being considered here. The dashed curve included illustrates the framework for a practical equalizer. So finally we can see that the transmission of a PAM signal imposes rather stringent requirement on the amplitude and phase responses of the channel. Because of the relatively short duration of the transmitted pulses, the noise performance of a PAM system can never be better than the baseband transmission. Accordingly, we find that for transmission over a long distance, PAM would be used only as a means of message processing for TDM, from which conversion to some other form of pulse modulation is subsequently made. The concept of time division multiplexing, it is discussed in the next session, next video. So in today's video, I have explained about the pulse amplitude modulation. What is the difference between natural sampling and flat top sampling? equations to elaborate on the PAM. How do we get the equations? How do we obtain the sinc function? And how do we do the demodulation? In the demodulation side, we have a reconstruction filter and the equalizer to get back the original message signal M of t. So while doing the sampling, in order to get PAM, we need to be very careful about two conditions. One is the instantaneous sampling, another one is the length of the duration of each sample. So keeping these two in mind, we need to get the sampling done. In the next lecture or in the next video, I'll be explaining about time division multiplexing. One main application of PAM is it will process the data or it will prepare the data so that it becomes a perfect input for a TDM application. So before going for the TDM, we need to understand the PAM. So in TDM, it is being done in the lab also. TDM experiment, before that we'll do the PAM. So we'll get a sample version of the message signal, and then that input is fed to the TDM experiment. So sampling theorem provides the basis for transmitting the information contained in the band limited message signal M of t as a sequence of samples of M of t taken uniformly at a rate that is usually greater than the Nyquist criterion. The important feature what you need to note in sampling process is conservation of time. That is the transmission of the message samples. It engages the communication channel only for a fraction of sampling interval on a periodic basis. And in this way, some of the time interval between the adjacent samples is cleared by the other independent message source on a time basis. This type we call it as a TDM, and this will be explained in the next video with a neat block diagram, and also I'll be explaining about pulse position modulation, its generation and its detection, how the noise in ppm affects the system, and briefly I'll give a formula for FOM of that system, and then how do we do the bandwidth noise trade-off. Thank you.